Hi everyone, thanks for taking the time to attending this talk. My name is Jinsheng Li. I work at Alibaba, mainly focused on Flink SQL. I am also a committer of Apache Flink and Iceberg. Today, my colleague Ray and I want to talk about Flink SQL, unified streaming and batch for Hive integration. Our contents are mainly divided into four aspects. First, difficulties of real-time in data warehouse. Second, Flink SQL unified streaming and batch. Third, demo. Fourth, summary and future. The above figure is a typical offline warehouse. Suppose the company has a large amount of data and needs to output a report every day or output it to business database. First, the inputs of warehouse can be roughly divided into two types. One is binlog of OLTP database. The other is logging in the business system. The login data can be collected by Fluent and other tools, and then put into the data warehouse. Then, with the increasing number of services, the tables in data warehouse can be abstracted. The advantage of abstraction is better management and more efficient data reuse and computation reuse. So the data warehouse is divided into multiple layers, like detail layer, middle layer, service layer, and else. Each layer stores data tables, and the data tables are converted by Hive SQL. We can call it ETL. And Hive ETL is just static computation. For continuous computation, we need workflow and batch relationship management. As mentioned above, we need tools for warehouse data ingestion, and we also need workflow tool. First, Fluent is used to data ingestion to file system, but there are some problems. First of all, its fault tolerance may not guarantee the exact ones. Secondly, custom logic is not easy to write. In warehouse, what we need is SQL. Third, it does not have good scalability. When the data increases sharply, it is difficult to increase the original partition number. Second, Airflow is used to workflow, but scheduling jobs will bring cascading computation delay. For example, the computation of yesterday's data from 1 o'clock a.m. may not be completed until 6 o'clock a.m. And it cannot guarantee that the data can be completely ready within the set scheduling time. In addition, cascaded computation will also bring complex blood relationship management problems. Batch computation of layered tasks may suddenly fill the cluster resources. Therefore, we are required to consider the load management, which will increase the burden on the business. So, real-time data warehouse comes. The real-time data warehouse is changed from Hive plus file system to Kafka. The ETL is based on the Flink streaming processing. At this time, there's no scheduling and blood relationship management problems. Through real-time continuous incremental updates, the final output to business database. Although the delay is reduced, we will face some other problems at this time. First, historical data is lost because Kafka is only a temporary storage medium. The data will have a time to live. For example, only 7 days data is saved, which will need to the loss of our historical data. Second, the cost of real-time computation is higher than that of offline computation. So what's next? Next is Lambda architecture. At this time, many people will choose a set of real-time and a set of offline warehouse, which do not interfere with each other, and separate the requirements according to whether the task needs to go through real-time requirements. So what's the problem of Lambda architecture? The architecture seems to solve all problems, but it also brings a lot of problems. First of all, two solutions make the same data source produce different computation results. The table structure of different levels may be inconsistent, and when the data is inconsistent, it is necessary to conduct comparison and troubleshooting. As the Lambda architecture goes farther and farther, the development team, table structure, table dependency, computation model, maybe they all may be split. The waste of resources is becoming higher and higher, and the cost of unification will be higher and higher. A real-time warehouse will consume so much resources and cannot retain historical data. Lambda architecture will seriously waste resources. So we should focus on unifying offline and real-time. Let's move on the next section of sharing, Flink SQL, unified streaming and batch. Flink has been committed to the unification of offline and real-time. First of all, unified metadata. In short, the metadata information of Kafka table is stored in the Hive metastore to unify the offline and real-time table meta. At present, there is no perfect persistent metastore in open source real-time computation. Hive metastore can not only save offline tables, but also bear the metastore capability of real-time computation. After the same metastore, the real-time and offline table structures can be designed to the same. The next step is sharing. With the same set of SQL, Flink itself provides batch and streaming unified ANSI SQL syntax, which can greatly reduce the burden of SQL developers and let users focus on the business logic. For the same engine, Flink uses a set of optimization and runtime framework. The big data engine at this stage is far from completely stable. So there are still many times when the user need conduct in-depth analysis and optimization. A set of engine can allow developers to focus on a single technology stack, avoiding the need to contact multiple technology stacks. Further, whether it can unify real-time and offline data to avoid data inconsistency and repeated storage and computation? Can we have some covalent interaction and conversion between real-time and offline? The real-time Kafka table should be synchronized to offline table in real time. First, as real-time historical data, offline table can help that there is no historical data in real-time data warehouse. Second, batch data ingestion provides real-time input for ad hoc query offline table. Third, batch workflow can be scheduled by streaming synchronized. At this time, the real-time and offline tables have been basically unified. Then the question arises, can the tables in Kafka and Hive share the same table? The idea is that there may be the following situations. Define a hybrid table in warehouse corresponding to Kafka and file system physical storage respectively. When the user performs the insert operation, it is naturally inserted into Kafka's real-time table. At the same time, another link is generated and automatically synchronized to the file system table. In this way, the table is very complete, not only to meet the real-time needs, but also have historical data. A SQL read, such as a hybrid source, is automatically routes to Hive's historical data and Kafka's real-time data according to the where condition after in your query statement. According to certain rules, the historical data of file system is read first, and then the real-time data of Kafka is read. But it is not implemented now. Let's move to the details of streaming file sync. Before Flink 1.11, streaming file sync was already available. It provides exactly one file sync. The checkpoint mechanism can ensure exactly once. The distributed computation is unreliable, and needs to be submitted through two-phase file renaming plus file renaming. It manages the organization and writing files. So the streaming file sync already provides exactly file sync function. But however, besides files, Hive table actually has partition management. What extensions have been made to table layer? In table layer, there's a partition-aware streaming file sync. Besides, table supports rich formats for Hive connector and file system connector. On the basis of streaming file sync, it adds a load to do partition commit. Which is partition commit? What is partition commit? Because our typical Hive tables are partition tables. When a partition is ready, it's necessary to notify downstream that the partition has been persisted and can be synchronized to Hive metastore. We need to effectively trigger specific partition commit at the right time. Generally speaking, the partition commit completes the writing of data and the meta of Hive partition store. Two aspects are described in detail below. What does the commit partition do? When commit partition? Because the streaming job is running continuously, when does the partition commit? The first is the first the first strategy is default policy persisting time, which is the current system time when the event is processed. However, it has obviously disadvantages, such as incomplete data, but it is simple. The recommendation policy is partition time, which can make semantics clear and data complete when commit. The partition field is obtained by the event time, that is the time when the event is generated. So if current time bigger than partition start time plus partition time size, okay, let's do partition commit. Next, we will introduce the specific effort of partition commit. The most direct way is write success file and add partition to Hive metastore. Flink has built-in support of Hive metastore and success file. If you choose metastore, you need to make sure that the table is a Hive table, because in this way, the framework can access metastore. The custom mechanism allows you to customize a class of partition commit policy. You can do such as trigger downstream scheduling or some statistical analysis. With partition commit, there's an intelligent file sync, but you can't set checkpoint interval too small because that will produce a lot of small file. Small files affect stability and performance. You need careful when business keys in the partition, and your jobs require large checkpoint interval, even 10 minutes. What is being developed in Flink 1.12 is in the subsequent processing of the writer. We can add the ability to merge files to compact files across tasks to ensure that at most one small file can be generated in a single checkpoint circle. We did some tests. We can adjust checkpoint interval from previous 10 minutes to 5 seconds, that making the file sync become real-time computing. Not only real-time data ingestion, Flink also brings join Hive dimension table and streaming real-time consumption of Hive table. We know that Flink supports dimension table join query for MySQL and HBase, JDBC and HBase. It maintains a LRU cache in the computation and fails to query MySQL or HBase. But what if you don't have ability to look up? Data is stored in the offline data warehouse, so we need to use Hive table to dimension join. Now Flink can also allow direct dimension table to join Hive table. The traditional Hive table only supports reading and computing in batch mode, but now we can use streaming mode to monitor the generation of partitions and files in Hive. That is, every piece of data can be consumed in real time. It is also a way of fully reusing Flink streaming SQL and can join other database, other Hive tables. Finally, it can be written to Hive table in real time through file writer. So what we do is make Hive faster and faster. Next, my colleague Ray Lee will talk about the use case of a batch streaming unified Hive warehouse and demonstrate how to use this feature. Thank you.
Hello everyone, my name is Ray. I'm a software engineer at Alibaba, and I've been focusing on the Flink Hive integration feature for the last 2 years. Today I'll give you some demo about how to use Flink to do some streaming process with a Hive warehouse. Okay, first let's think about what you can do with this batch streaming feature that Jingsong has just talked about. Take this use case for an example. Let's say you have a Kafka stream which contains order logs. You can ingest this stream into Flink and do some ETL on it. For example, you may want to join it with an offline user table to complement the orders with user information like user age. This offline user table may be a MySQL table, but starting from Flink 1.11, it can also be a Hive table if it's small enough to be loaded into memory. Next, the joining results can be written into a Hive warehouse in a near real-time fashion. And furthermore, you can have another Flink job to run some real-time analysis on this warehouse to produce results with very short latency. And of course, you can also have offline jobs to run batch analysis on the Hive warehouse with Flink 2. So as you can see, with the ability to support both batch and streaming workloads, you can have a unified warehouse and a unified execution engine, which will reduce the complexity and the cost of your platform. And note that all this can be done just with Flink SQL. You don't have to write a single line of Java or Scala code. Next, I'll show you some demos, and these demo videos are pre-recorded, and I'll go through them with you. Okay, here is a demo for streaming read and write. First, let me briefly talk about how to set up an environment to integrate Flink with Hive. I have installed Flink and Hive on my laptop and started HiveMet server. Then on the Flink side, we have to add some dependencies to connect to Hive. In prior versions, you have to add quite a few jars to connect to Hive, but starting from 1.11, we provide Hive connector Uber jars. You can pick up one Uber jar and put it in the lib folder, and that's it. There are 4 Uber jars like this to cover all the Hive versions we support. You can check out our document to find out which one to use. So next, we also need to configure a Hive catalog, and we need to do that in the SQL client YAML file. Okay, in the catalog section, you can configure a Hive catalog like this. With these 3 parameters, the name, type, and path to the HiveConf directory. And you can also configure a Hive module if you'd like to use Hive built-in functions. And in the execution part, we set planner to Blink because only Blink planner supports Hive connector. And we set type to streaming because we're going to run some streaming jobs for the Hive table. Okay, next we also need to enable checkpointing because streaming file sync commits data based on checkpoints. And to do that, we have to set a checkpoint interval in the Flink conf YAML file. Like this one here, we set the checkpoint interval to 30 seconds. Okay, and then we are good to start the Flink cluster. And the SQL client. Okay, now let's create the streaming source table. And for the sake of simplicity, I'll just use DataGen to mock the data. And the table has two columns, the ID and the timestamp. And the timestamp column serves as the event time. And the DataGen will generate records per five records per second, and the ID will be sequentially generated from 1 to 3000. And then let's create the destination Hive table. And the best way to create a Hive table in Flink is to use the Hive dialect. We can switch to Hive dialect by setting this property. Okay, then we can create the table. Okay, the table also has the ID column and the timestamp column. And the timestamp column here is a partition column. And for this table, we set the commit trigger to partition time and the commit policy to the metastore plus success file, and the delay to 1 minute. So each partition will contain 1 minute's worth of data. Okay, then we can start data ingestion into this table. Okay, note that we call data format on the event time here like this, so that we'll have partitions by minutes. Okay, the job has been submitted successfully. We can check on the web UI to verify that the job is running. Okay, and then we can verify that whether data has been written to the table folder. Okay, we can see that some data has been written into the desk table, and we can see if partitions are committed. We got one partition committed, and we can check the success file for this committed partition. Okay, as expected, the success file has been written for this partition. So that's in line with the commit policy we set. Next, we can start another Flink job to do streaming read on this table. And to do that, first let's switch back the dialect to Flink dialect. We set this property back to default. And then remember that we don't set streaming read properties when we create the table. But that's all right, because we can still use the dynamic table hints to enable streaming read for this table. Okay, note that here we set the consumer order to partition time, and we check for new partitions every 30 seconds. And we also set an offset to start with, so we are only interested in partitions that arrive after this point of time. Okay. Okay, the job has been submitted, but data is not retrieved yet. We can check if the partitions are committed. We can see that the partition we are interested in has been committed. So next we have to wait for the reading job to discover this partition. Okay, new data has been retrieved back, and it's in line with the offset we set for this table. Okay, so much for the demo of streaming read and write. You can cancel this data ingestion job on the web UI. Okay. Next, let me show you a demo about temporal joining a Hive table. Let's say we have a Hive dimension table like this with two columns, key and value. And since it's a temporal table, we can also set the cache TTL. So after this TTL, the cache will expire and the table will be reloaded. Okay, now let's load some data into this this dimension table, like these 5 records. Okay, now we have the dimension table ready, and for the streaming source table, again, I will just use datagen source. So the datagen will randomly generate keys in the range of 1 to 10. And then we can submit the query to perform the temporal join for these 2 tables. And note that at the moment, only processing time is supported for temporal joining. We can see the joining is producing some results. Now let's update our dimension table. We update the key 3, the value for key 3. And we also add a new record with key 10. Okay. Let's load this new data into our dimension table. Okay, the data has been loaded into the dimension table, and we also let it to override the old data. So what we are going to do now is to wait for the cache to expire, and then the dimension table will be reloaded to get the updated data. Let's wait for a bit. Okay, we can see the join is producing results with updated records, which means the dimension table has been reloaded. Okay, so that's it for the demo. Okay, to recap this part, with the unified batch and streaming feature, Flink can do real-time data ingestion into Hive, and that can also be the real-time input for ad hoc queries. And this real-time pipeline will speed up your overall ETL process. Other features include joining with real-time data with offline table, or you can leverage the flexibility of partition commit to run customized workloads, such as to schedule other batch jobs. So in the future, we will continue to improve the usability and the experience of Flink Hive integration. And here list some features we have in mind. For example, we'll implement small file compaction. Therefore, when you write streaming data into Hive, you don't have to do trade-off between small files and the latency. We also aim to improve the Hive dialect feature so that Flink can support queries written in Hive syntax. Then users will be able to run the good old Hive queries with when using Flink SQL to do batch or even streaming process against their Hive warehouse. And if you are interested in this feature, please feel free to contact us in the community to let us know what new features you want or report a bug. We will be glad to help, and perhaps we can adjust this feature list according to your requirements. Okay, so much for the talk today. Thank you all for your time.